A quick introduction to hashing. So what is hashing? Hashing is basically a way where we can map data to a unique value. And the idea is we want to have a hash function that takes in this data, processes each little bit of the data, and uses each bit of data in order to produce some sort of hash code in the end. So why hashing? Hashing is a quick and easy way to look up data. It also can easily detect duplicates in our data structure. So the idea is um, each bit of data produces a unique hash code. And hopefully, if we do run into collisions where bits of data are different from one another, but they hash to the same thing, hopefully we'll be able to address that with some open addressing or separate chaining, which we'll go over in future videos. That's how we can resolve the collisions there. So where is it used? Well, hash tables, hash maps, hash trees. We also use it in caches because caches are used for quick and easy access to temporary bits of data. Um, we also use it for finding similar bits of information. So if our hash function is good and we happen to have two data sets that tend to hash to the same hash code, then hopefully the files or the information that the data sets give us are very similar to one another. If they're not very similar, then we need to rework our hash function. We also use in cryptography where we can say type in a username and a password, and each one of those gets hashed to a specific value, and then we decrypt it using another hash function that can hopefully return to us the right value data set. So what makes a good hash function? We kind of went over this a little bit in an earlier slide here, but what we should be doing with our hash code is using every bit of data that's passed in. Odds are some of the hash codes are going to be, hashing to the exact same thing. That's just something that's bound to happen. It's inevitable. But hopefully, if our hash function is good enough, each data set should produce a unique hash code to it. And likewise, similar data sets should produce unique hash codes. Okay, so here's a little bit of a hashing example. Typically, for this example, we're going to be using a variable length string, meaning that we're going to be using strings that vary in terms of length. Some of them could be very short, some of them could be very long. We're going to use polynomials because polynomials give us a great distribution of the hash codes. The reason why that's so is polynomials are numbers that can only be divisible by themselves and by 1. If we use, say, something like 9, which is an odd number and is divisible by 3, odds are we could have multiple different sets of data that could be hashing to the same values. So that's not good. So in this function by Mark Allen Weiss from Data Structures and Algorithm Analysis in Java, he says what we're going to do is we're going to start off by setting our hash code to 0. And what we're going to do is use each character in our string and then produce an individual hash code based off of the polynomial that we've selected and the character in terms of its ASCII value here. And we're just going to multiply the hash code by the polynomial and then add on the ASCII value of the character at the end. And then he says after we've looped through the entire string, what we want to do is we want to modify our hash code by modding it by the table size in order to actually get it to fit somewhere in the table. And here's the thing where we have this function called ensure no overflow and we pass in the hash code. Basically, ensure no overflow guarantees that if our hash code happens to be too large of an integer, meaning that we can end up with some large negative value because of the way the integer is represented, the idea is that it'll basically convert that big number back into a valid positive number in our table that we're using. And then at the end, we return the hash code. So here's some commonly used hash functions here. So the idea of perfect hashing, is that we use each bit of data and it's hashed to a different value. So in this last example here, it happens to do so. and it falls into the line in order of uniform data distribution. So for the most part, hopefully what it guarantees is that all of our data is spread amongst the table in such a way that we don't have any erroneous gaps once we're done hashing, or we don't have any collisions overall. So variable length hashing, it's what we used here where we went through the entirety of each character and basically used its bit of information in order to produce the hash code. Universal hashing is pretty cool because what we can do is we can basically have a set of algorithms that implement various hash functions like cuckoo hashing or variable length hashing. And what our universal hashing algorithm will do is it'll try to determine, based off of the data set that we're given, what is the best hash function to use, so that we can try to ultimately get to something like perfect hashing. Uh, so here are some references in case you want to learn a bit more or figure out what I used. So special thanks to Mark Allen here and Wikipedia. Also, Professor Zan is also great. His slides are up online. The video or the slides that I used were from the summer of 2016, in case you're wondering. But otherwise, hopefully we'll see you guys next time, and in upcoming videos, hopefully we'll go over an implementation of the open addressing and separate chaining implementations of a hash table. Well, hope you guys learned something, and see you next time.